In this presentation, we introduce the double-loop quasi-Monte Carlo estimator for nested integration. By nested integration, we mean that a function g of y and x is integrated with respect to x, a nonlinear function f is then applied, and this is integrated again with respect to y. Such problems are common in engineering, medical decision-making, and mathematical finance. For the case where neither integral has a closed-form solution, the standard approach is to use the Monte Carlo method to approximate both integrals. To reduce the computational cost of such estimators, we propose to use the quasi-Monte Carlo method instead. The quasi-Monte Carlo method uses deterministic points from a low-discrepancy sequence, which are then randomized to simplify error estimates and guarantee other useful properties. This can reduce the computational work of the double-loop Monte Carlo estimator by up to 1.5 orders of magnitude. We now use this estimator to approximate the expected information gain of an experiment. We model observation data y as a deterministic function capital G plus observation noise epsilon. The expected information gain of the experiment is then given by a nested integral, where the parameter of interest is denoted by theta and the design parameter is denoted by xi. The goal is to optimize the expected information gain with regard to xi and ensure that the obtained data is most informative. We can use the Laplace approximation to further improve the quality of these estimators. We now show an application from thermoelasticity where we have a square domain with a circular exclusion at the lower left corner where a heat source is applied. The increase in temperature and displacement are then measured at sensors on the top boundary. This allows us to estimate certain physical properties of the material. And as it turns out, the experiment is most informative for intermediate observation times and sensor locations close to the circular exclusion.